Okay, so we've had a look at work and energy in a closed system, that being one where there's no friction, no applied force acting, and we can consider in those cases, as you probably know, that E mech initial is equal to E mech final. Nice and simple setup. But what happens if there is an external force acting? For example, the force applied or the force of friction. Then we've got to deal with the whole picture. So the kind of example we'd be dealing with is, for example, a car driving up a slope like that, where the engine is obviously acting as an applied force. There's very likely to be friction in this scenario. So what we need to do is look at the whole picture now of work that's being done. In other words, Wnet, the overall work. So Wnet, in order to get that, we need to look at every single one of the forces that could potentially be doing work, and so that we can add them all together. So the engine is our applied force. Friction is going to be pulling the car, opposing the motion, pulling down the slope in this case. The force of gravity acting vertically downwards, and the normal force is going to be pushing perpendicular to the plane. So those are our four forces acting on the car. Now, in order to be able to put that into an equation, we simply add them all up. So that will give us an expression for Wnet. So Wnet is equal to WA, the work done by the engine, WF, the work done by friction, which is of course going to be negative, the work done by gravity, also negative in this case, and if we wanted to, we could correctly say the work done by the normal, but we never need to worry about that. Why? Because the normal is always at 90 degrees and therefore never does any work. It's the laziest of forces. Okay, so our work net is going to be an expression like that from the diagram. But that's not the only way that we can find work net, because there's another way that we can, as you probably well know, the work energy theorem, that the overall work done on an object is going to be equal to the delta K, the change in kinetic energy. So it's a nice simple equation. We can just write that down directly from your formula sheet. And now we've got two different ways of finding Wnet. We've got the sum of the works and we've got delta K. So we can bring them together. So your working would typically start with the work energy theorem. That'll be worth a mark just in itself. Then you expand it out for all the different works that are being done by the different forces, and then put your delta K on the right hand side. Now, it depends very much on the question as to how this is going to go from here. But as an example, you would elaborate each one out. The work done by the applied force is FA delta X cos theta, theta being 0 in that case. FF delta X cos theta for the friction, theta being 180 in that case. And for the work done by gravity, probably the easiest way to do it is MGH cos theta, where again, if it's going up the hill, cos theta is likely to be at 180. I'm not going to go into too much detail as to why that works, but that is a nice little shortcut. And then delta K. Now, one little hint is if you're given the phrase in the question that the object is going at a constant velocity, well, that is a major bonus, because that tells you that there is no change in speed, no change in K, and therefore delta K would be equal to 0. It makes your life a lot easier. So that's the kind of a working that you would do. You're going to need to apply this in various different circumstances to get used to it. There's one other little trick that you can use depending on the question. You might be given a case where you know the Fnet, or you have worked out the Fnet, in which case it's dead easy, because Wnet is simply equal to Fnet delta X cos theta. So that's kind of a little shortcut if you end up with a question like that. So those are the different scenarios. It's a lot of problem solving, and they can really give a variety of different contexts, from our car driving up a slope or down a slope to a box being pulled along the ground. There's even one with a guy being pulled up in a helicopter, and there's friction involved and all sorts. So they can throw it at you from all kinds of different angles, and you've got to get used to being able to do whichever the problem is. So do plenty of examples, and I'm sure you're going to be able to nail it. Good luck.